So the table is all we're going to complete on this side, though at the bottom it has this fundamental theorem of algebra. We're not going to fill that in. We're going to do the number of zeros of a polynomial, which is a part of the fundamental theorem of algebra and the part that we focus on the most. So we're just going to skip to that next page now. And for the number of zeros of a polynomial, we're going to write down that a polynomial of degree n, where n is greater than or equal to 1, has a total of n zeros if you count multiplicities. So in our previous page of notes, we had a second degree, and it had 2 real zeros, each one having a multiplicity of 1. So 2 zeros, multiplicity, each had 1. Here we had only 1 real zero, but it had a multiplicity of 2. And that's why it was still a second degree. My multiplicities add up to 2. My multiplicities add up to 2. Here I've got no real zeros, but 2 complex. Each one, we didn't write that in the table. Each of these has a multiplicity of 1. And that still adds up to my 2 total solutions for a second degree. So the degree determines the number of zeros if you count multiplicities. Because sometimes there's only one solution, but it has a multiplicity of 2. Sometimes it can have a multiplicity of 3. Maybe that factor occurs 3 times. So let's look at this example 1. It says for each polynomial, find the zeros, real and or complex, and their multiplicities. So this is already in factored form, so I can say that x minus 4 equals 0, x plus 1 could equal 0, and 2x minus 3 could equal 0. When I solve each of these, and I would add 3 and divide by 2, so I would get x equals 3 halves. These are my zeros. Because this factor occurs twice, this has a multiplicity of 2. Because this factor occurs 3 times, this has a multiplicity of 3. And this factor only occurs once, so it has a multiplicity of 1. Let's look at this next one. I'm going to see if I can do a little factoring here. I'm going to pull out that each of these can be divided by x cubed. I'm going to pull that x cubed out. And I'm left with x squared minus 6x plus 9. Since this has a leading coefficient of 1, I don't need to use slide and divide. I can simply use my diamond method. I need to multiply to 9 and add to negative 6. Well, my factors of 9 are 1 and 9, 3 and 3. Is there any way I can make negative 6? Sure is. Negative 3 and negative 3. Adds to negative 6, multiplies to positive 9. So I get x minus 3 and x minus 3. So now I'm in factored form, just like letter A was. So x cubed, for that to be 0, x would just have to be 0. X minus 3 to be 0, x would be 3. Since this is x to the third, this has a multiplicity of 3. Since x minus 3 happens twice, this has a multiplicity of 2. Let's go to this next one here. I know that my only factors of 5 are 1 and 5, and there's no way to make 2, which means this is not factorable. I'm going to try quadratic formula. So A is 1, B is 2, C is 5, X equals opposite of B plus or minus the square root of B squared minus 4 times 1 times 5, all divided by 2 times 1. So that negative 2 plus or minus. I'm going to put this in my calculator. Actually, I can do this in my head. 4 minus 20 is negative 16. So I get negative 2 plus or minus 4i divided by 2. Therefore, each of these can be divided by 2, and I get negative 1 plus or minus 2i. So negative 1 plus 2i is a 0 with a multiplicity of 1. Because this is an x squared, negative 1 minus 2i is my other factor. Since I have two factors and I can only have, two solutions, and I can only have 2 total, well, each of these must only occur one time. So I have 2 solutions, each occurring once. And we are not doing this bottom part. Okay. That's where we're going to end right there with those notes. Now we come to the conjugate zeros theorem. This is a really important theorem as well that we're going to be using a lot. And it says when a polynomial has real coefficients, if a plus bi is a factor, then a minus bi is also, actually it wouldn't be, not a factor, a 0 is what I meant to say, a 0, which would then, you could write a factor. But if a plus bi is a 0, then a minus bi is also a 0. We could substitute the word solution here. We can't substitute the word x-intercept because a plus bi is complex, so it's not on the x-axis. But if a plus bi is a 0 or solution, then a minus bi is also a 0 or solution. So let's see why this is so important. We're given this equation, this polynomial, and we're asked to verify that 3i is a 0 of this polynomial. Well, if 3i is a 0, then negative 3i must also be a 0. According to our conjugate, because this is 0 plus 3i, so the other one would be 0 minus 3i, which means if 3i is a 0, negative 3i is a 0. If we know zeros, then we automatically know factors. Therefore, x minus 3i is a factor. And for this one, x plus 3i, because it's always x minus the 0, is a factor. Therefore, x minus 3i times x plus 3i, I can multiply them together, is a factor. I mean, think about it. If 2 is a factor of something and 3 is a factor of something, then 2 times 3 or 6 must also be a factor. So I'm going to FOIL this, and I get x squared plus 3i minus 3i plus 3ix minus 3ix minus 9I squared. These cancel, and this becomes plus 9, because negative 9 times negative 1. So x squared plus 9 is a factor. Well, if x squared plus 9 is a factor, I should be able to put x squared plus 9 into 2x cubed minus x squared plus 18x minus 9, and my remainder should be 0. Because if something's a factor, that means when you divide whatever it's a factor of by that factor, you get 0. For instance, 6 is a factor of 18. 18 divided by 6 is 3, with no remainder. Now, if I'm going to divide this, I am going to need to put a placeholder here. So that would be x squared plus 0x plus 9. Focus on the first. 2x cubed divided by x squared is 2x. Then multiply 2x by each of these, and I get 2x cubed plus 0x squared plus 18x. These cancel, but actually before I do that I need to change colors. Let me grab my red pen. Because I'm subtracting, I change all my signs. Now I can add up. Negative x squared, these cancel, minus 9. Focus on the first. Negative x squared divided by x squared is negative 1. And I get negative x squared. And I get negative 9. When I subtract, I change my signs. And I got a remainder of 0. Therefore, I have verified that 3i is a 0, because if 3i was a 0, negative 3i was a 0, which means these factors are factors, and I showed that when I divided by those factors, I got a remainder of 0. The next question says find the remaining zeros. Well, I can do that by, well, I've almost already done that. I know that my other 0 is negative 3i. I had already said that. Right here I had already said that negative 3i must also be a 0. And because of this factor, 2x minus 1 equaling 0, add 1. Divide by 2, x equals 1/2. X equals negative 3i, and it says end their multiplicities. We were already told that x equals 3i was a 0. That was given. And there's 3 solutions, and this is an x to the third. So each one has a multiplicity of 1. Which adds up to 3 total solutions. This process here, where I give you one complex solution, which automatically gives you the second, and then you can multiply, divide, and find the third 0, this is something you're going to have to do on your test. So we're going to have to practice this a little bit more.